Dr. Mack, we're at the last episode of our podcast.
We are at the last, and I am so sad. I've been really enjoying these conversations.
It's meant so much to me. I've never learned nearly this much from a project, and I just have really treasured our conversations, and I'm looking forward to this one because this time we get to go to the end.
Yeah. The real end, the absolute end.
Well, we have finally arrived. Katie has walked us through the entire history of the universe in just 10 delightful and sometimes dread-inducing episodes. She carried us through cosmic inflation, recombination, the Dark Ages, the formation of the first stars, and she did all of this with great patience and camaraderie. She even taught us about what the future holds for our universe. But all things must end, and that includes both this podcast and, the universe. While the podcast conclusion is simple and finite, the universe is much less so. We can't predict exactly how it will all end, but there are a few strong possibilities, some more disconcerting than others.
This is one of the things that people ask me about, does the universe have to end? And as far as we know, the laws of physics just are not okay with the idea of everything kind of staying as it is forever. I mean, one of the things that you run into is the second law of thermodynamics, and that's this statement that entropy, which is sort of another way of thinking about disorder, increases into the future. That's why you can't have a perpetual motion machine or something like that. If you make an extremely efficient, spinning wheel or something, at some point there's going to be a little bit of energy loss through heat to the atmosphere, and it's going to slow down and it's going to stop, right? And that's the second law of thermodynamics, that everything kind of evolves toward decay one way or another. And so you can't really get away from that, even if the universe were not expanding, even if everything were kind of staying stable in some sense, things would get eventually less livable. Stars would use up their fuel and burn out, and particles would decay, and you would eventually get to something that looks like an end. And we've seen the evolution of the universe so far has been changing. The livability of the cosmos has been changing over time. The very beginning, it wasn't livable because it was too hot and dense and plasma everywhere. And then there was a stage of this peak of star formation, cosmic noon. There was lots of stuff going on, galaxies and everything. And since then, it's been evolving toward sort of cooling down phase, right? The amount of star formation has reduced. Galaxies are sort of drifting apart from each other.
Except for Andromeda.
Yeah. Yeah, the distant galaxies are drifting apart.
Easy for you to say galaxies are drifting apart from each other. We're going to get hit by one.
Yes. Yeah.
That really bummed me out when I found out about that. But it turns out that it's just one bummer among many.
I mean, it'll be cool. It'll be, impressive when it happens.
Yeah. Well, to be fair, it won't be my issue, and it likely won't be our issue as a species.
Yeah. Some distant civilization will get to add one more, cool interacting set of galaxies to their catalog. I mean, it'll be neat. Anyway, there just isn't really a mechanism to replenish the order in the universe, right? Things will evolve somehow toward an end. And when I say an end of the universe, this is the other thing that I want to emphasize about the end of the universe, is that I don't necessarily mean existence of all kind comes to an end. I mean that everything that's in the universe that, has any kind of structure is destroyed, right? That is inevitable. Whichever way you go, that happens. There are some ends of the universe in which, in some sense, space-time still exists, and maybe some energy still exists, but everything that is now is destroyed. That will happen, as far as we know, as in the way that we understand physics right now.
Okay. So walk me through, our sun is a white dwarf. We are probably pollution inside that white dwarf. and almost all the stars that have ever been born or will ever be born are already burning.
Yes, or have already burned out.
And then what happens?
So I think last time we talked about how as the expansion continues, distant galaxies get farther and farther away and move away more and more quickly, and so we stop being able to see them.
Right. The JWST, instead of seeing what it's seeing, will see nothing.
Yeah, so you get to a point where we don't have any view of the distant universe. And we don't have any view of like the past of the universe either, because we can't see things in the distance, so we can't see things in the past. We can only kind of see our immediate surroundings, and everything else is just dark. So you get to a point where there's not much to look at. And then what happens from there, I mean, that's like 100 billion years. That's a reasonable extrapolation from what we know now. But there are kind of different possibilities that can happen that depend partially on what dark energy is doing. And those can change the story either after that stage or maybe somewhat before. But the idea that we do get to a point where we're just looking out into the dark is pretty likely based on our current understanding.
Okay.
But because we don't know what dark energy is, and we don't know how it's going to change over time, potentially, there are a few possibilities that are still kind of in play, at least in terms of like matching our observations as we extrapolate into the future. In my book, I talked about 5 different endings of the universe. So I can just kind of go through those. 3 of them have to do with what dark energy is doing, and then 2 are kind of wild cards
Great.
for other things. So, okay, so when we've talked about dark energy before, we've talked about the fact that our kind of best guess about dark energy is that it's a cosmological constant. It's something that Einstein first wrote down, and he wrote it down in the service of, keeping the universe static. So, he didn't know that the universe was expanding, and there had to be some reason why all the stars didn't fall down on us, basically, was the way he was thinking, because he knew that gravity should attract everything together. And so he put in this term in his equations of gravity that kind of added a sort of pushing apart in addition to the pulling together of gravity. And so it imbues every bit of space-time with this little bit of kind of swelling or stretchiness, so that in the picture that he was putting together, all the gravity of all the stuff falling together would be perfectly balanced by this pushing apart that's like just inherent to space-time. And that would keep the universe static.
But it turns out it's not static because dark energy and gravity don't perfectly match each other?
Well, it's not static. I mean, the universe is expanding. So when it was found that the universe was expanding, that threw out the whole static idea. And that naturally explained why everything hasn't fallen into a big clump, because it's been expanding since the beginning. And so, you can think of it in some sense as there's a momentum of things moving apart. So they threw out, Einstein threw out the cosmological constant when it was discovered the universe was expanding, didn't need anything to hold the stars up anymore. But when we discovered that the expansion of the universe was speeding up, then we had to have some reason why the expansion was speeding up, because gravity wouldn't do that.
Right. Okay.
In a universe with just stuff and gravity, the gravity of everything should be putting the brakes on the expansion, right? Maybe the expansion is happening, but everything is pulling together, and it should slow down the expansion. But when it was found that the expansion was not slowing down, astronomers had to throw in something to make that the expansion accelerate, and the cosmological constant was right there, right? It was this mechanism that was already hypothesized. You put it into the equations. Space-time has a little bit of stretchiness in it. And that means that when you get to a certain point, as the expansion is set off by the Big Bang, everything's moving away from everything else. At some point, and it is slowing down at the beginning because the gravity is working to slow down the expansion. Things get far enough apart that gravity is very weak, then the stretchiness of space kind of takes over as the dominant effect, and that makes everything speed up, accelerate, and that makes the expansion accelerate. So the idea of a cosmological constant fits the data pretty well. There are very few sort of pieces of data that don't seem to favor just the idea that the expansion is this cosmological constant, which is where, every little bit of space has a little bit of stretchiness built in. It's the same amount everywhere. So, it's called constant because the density of this stretchiness stuff is constant, right? The density of cosmological constant is constant. There's more space, there's more cosmological constant. It becomes more important over time. That's an idea for what this, so-called dark energy could be, is whatever it is that's making the universe expand faster. We call that dark energy. Maybe it's a cosmological constant. But it could be something else, right? And if it's something else, if it's like some kind of new dynamical field, energy field in the universe, like we have hypotheses for energy fields that could affect space-time expansion. And you can set something up where you have some kind of an energy field in the universe that causes space-time to expand faster. And we invoke that when we talk about cosmic inflation. So this very rapid expansion of the very early universe, that we say was driven by an energy field. We call it the inflaton field. And it's
the worst.
Yeah, I know, it's terrible. But it's what we call a scalar field, meaning that it's a field with like a certain value associated with it everywhere, which is, I'm only getting into this because I'm going to come back to scalar fields later, but a scalar field is like if you look at the temperature in a room, you can assign a temperature to every point in the room. That's a scalar field. You're just giving a number everywhere. Okay, and so a scalar field is a field where there's just a number everywhere. Unlike, an electric field or something where there's a number, but there's also a direction of the field in every direction. That's a vector field.
Okay. So a scalar field is the temperature the same in every part of the room?
Not necessarily.
But so the number could be different that's associated with it, but there's a number associated with every part of the room, and that's the field.
Yeah.
But it's not heading in any particular direction.
Exactly.
Okay.
Yeah. Whereas you can measure the electric field everywhere in a room, but it'd be pointing some direction, right?
Right. It'd be going somewhere.
Yeah.
Okay.
Anyway, so there could be a scalar field in the universe that is the dark energy.
Right.
That is affecting the expansion rate. And it could just happen to look like a cosmological constant in the way that it's acting on the universe right now. That doesn't seem so likely, but we can't rule it out. I mean, to me, it doesn't seem so likely. To others, it seems like the most likely thing. It varies, right? Like how you evaluate this stuff.
So because we don't know what dark energy is, there's a level of ambiguity in the deep, deep future of the universe, but we can kind of put together a certain set of possibilities based on what dark energy might be. And that's really what you do in your book, The End of Everything, Astrophysically Speaking, is look at these different versions of what the end of the universe might look like, depending on what dark energy proves to be.
Yes, exactly. And so there are kind of three things the dark energy could do, right? It could become more powerful in its sort of expansionness, right? It could become less powerful in its expansionness, maybe even like cause contraction instead, if it's something that's just messing with the way space-time moves. Or it could be constant, the way that a cosmological constant is.
So does the universe have to end? Unfortunately, the laws of physics say yes, at least in the way we think of the universe as containing structure and order. The question is not if, but how. And to answer that question, it might help us to look at dark energy, that mysterious force causing the universe to expand faster, which Einstein accidentally took note of when he hypothesized the cosmological constant. But dark energy could also take the form of a scalar field. So because we don't know what dark energy is or how it might change, we have a few different potential options to consider for how all this ends.
So right now, the dark energy is causing the expansion to accelerate, but it could fade away in some sense, or it could be something that changes over time. It could even be something that somehow turns around and causes compression. So there's a little bit of a hint, and this is very recent, but there's a little bit of a hint from a recent galaxy survey called DESI, the Dark Energy Spectroscopic Instrument. They did a galaxy survey.
You guys love your acronyms.
I know.
Love an acronym over there.
Yeah. So they, in their first data release, they found sort of tentative indications that maybe dark energy is getting less powerful over time.
Oh.
It's not clear because it's the first data release. It's not the significance of the result is not high. It involves bringing in data from other surveys as well to get this result. But, it's possible that dark energy is somehow getting less powerful over time. If it got so much less powerful that it not only turned off but started to reverse, and I don't know what kind of theories will do this, but you can imagine a theory that could do this. You could imagine a situation where the expansion of the universe stops accelerating, stops happening, where the expansion stops, and everything starts falling together again. And then you would end up with what's called a big crunch.
Good name.
Yes, yeah. And the big crunch, even before dark energy was thought about, the big crunch was an idea that was popular, like in the 1960s, when we knew the universe was expanding, but we didn't know if it was going to continue expanding forever or stop or turn around. And the data at the time, which was not as accurate as the data we have now, sort of hinted toward collapse, right? Hinted toward the idea that the expansion was going to someday stop and turn around. Just basically the idea was that the Big Bang set off the expansion, but there's so much matter in the universe that it's going to slow the expansion down so much that it'll stop and everything will fall together again. That was the hypothesis. And now that we know that the expansion is accelerating, that doesn't seem to make sense. There's not enough matter to do that, but maybe dark energy could make that turn around. So to me, I'm going to talk about 5 different ends of the universe. To me, the big crunch is the scariest one.
Really?
I don't think it's very likely. It's not something where the theories are really pushing that direction in any way. But to me, it's the scariest one for a couple of reasons. One, you would see it coming, right? So at some point, we would start to measure the redshifts of distant galaxies and clusters and things. And we would start to see that things are not redshifted anymore. The light isn't being stretched out by the expansion anymore. It's starting to be blue shifted. So the light is being compressed to higher frequencies.
And then that these galaxies are coming for you.
Yeah.
The way that I know Andromeda is coming for us, thanks to you. And so all of the galaxies are kind of coming for you.
Yeah, so you would see everything's coming for you. And so the fact that you're going to get hit by a bunch of galaxies is disconcerting, but it's actually worse than that because also space is going to get hotter.
Oh.
So, we talked about the cosmic microwave background back in the early days of the universe when everything was hot and dense. Space itself was hot. It was filled with hot plasma. And we can see that when we look at the cosmic microwave background. We can look far enough away to see that hot, glowing universe. So if you compress the universe again, then all of that energy gets compressed again, and you start to get back toward that hot, glowing plasma stage where just everything, all the light from the cosmic microwave background that we see now has been redshifted a lot. It's been stretched out by the expansion of the universe to microwave wavelengths, but it would be compressed again until it came back to visible, ultraviolet wavelengths, hotter and hotter, higher and higher energy light. Like
climate change, but for the universe.
Yeah, but it's even worse because it's not just the background light that would be compressed and hardened radiation. It's also all of the light from all the stars that have ever shone, right? All of the supernova explosions, all the black hole outflows, all these high energy photons that have been thrown out into the universe because of all of the astrophysics that's ever happened. All of that light would also be compressed into a smaller space and also be shifted into higher frequencies, harder radiation. And so it's been calculated. There's Martin Rees, who's the Astronomer Royal of the UK, I guess, or of England. I'm not sure. Anyway, he did a paper in, the early 70s or something, maybe 69, where he calculated what would happen in a big crunch and found that you can get to a point where the ambient radiation in space is so hot and so high frequency and so there's such high density of radiation that at some point it would start to ignite thermonuclear explosions on the surfaces of stars. There'd just be so much energy in space.
Oh, God.
Yeah. Yeah. So, the idea of existing in a universe where that's coming, that's terrifying to me. I do not like that.
Okay. I agree. That thermonuclear explosions happening on the surface of all the stars sounds stressful. Agreed. But, counter-argument, is it possible that in a big crunch, things go back to being a hot, dense soup for a long time, and then eventually the soup becomes hot and dense enough that there's another Big Bang. An accordion-style recreation of the universe.
So in a generic Big Crunch, you don't have a new beginning. It just ends. It goes to a singularity, and you can't really do much with that. That's a hard stop in an equation. That's a full stop at the end of that sentence. Right? It's just, and we'll talk later about different ideas for cosmologies that do have a new beginning, but a standard Big Crunch is not one of them.
You know what I just realized when you said that?
Yeah.
I realized that in some like future Wikipedia, some theoretical Wikipedia, like I always think the most beautiful two words in English are from the Wikipedia article on smallpox, which begins, smallpox was.
Nice. Yeah.
I just think this is the most impressive thing we've ever done, right?
Yeah, yeah.
But given the fullness of time, every Wikipedia article will be past tense.
Yeah, yeah.
So, yeah, here's to doing the best job that we can do to make the ones we want to be past tense in terms of Wikipedia articles past tense, and the ones we want to be present tense Wikipedia articles present tense.
Sounds good, yeah. So right now, something like 70% of the energy density of the universe is in dark energy, whatever dark energy is. In the past, it was less because the universe was more dense with matter, and so most of the energy density of the universe was in matter. At the very beginning, it was mostly radiation. You know, most of the energy density of the universe was radiation. So we had a radiation era, we had a matter era. Now we're really in a dark energy era, right? So right now, the bulk of the sort of evolution of the universe is governed by dark energy. We call it dark energy domination. Okay.
Oh, that's good. That's really good. I feel like you should be credited for that.
It's a good one. I like that one. Yeah. So, you know, if dark energy is a cosmological constant, then we know how that's going to go. Like we get to that stage where in 100 billion years we can't see galaxies anymore, and everything just keeps diffusing. The accelerated expansion becomes, you know, just that's what's happening. And the matter in the universe becomes less and less and less and less important. Right now, you know, matter is something like 30% of the universe. It'll become, you know, 5% of the universe. It'll become 1% of the universe. It'll become just very unimportant. And we'll evolve toward a universe that's just got this accelerated expansion, exponential expansion going. And as that happens, like, you know, all of the other galaxies will be out of contact with us in the sense of being too far away to see or moving away too quickly to see. There's a certain distance out to which we will be able to get information and not beyond that. And the stuff in our galaxy, what's left of our galaxy, you know, the sort of milkdromata, the combination of Andromeda and us, those stars will be burning out, right? So the stars will burn out, you know, trillions of years. The stars will be burning out. Even the small ones that burn real slow, the red dwarfs, those will start to burn out. The white dwarfs will fade away. They'll get cooled and fade away. Black holes will start to evaporate. So black holes, we talked about this a little bit in the black hole episode, but black holes have this Hawking evaporation process where they can lose mass through radiation. That'll happen to all the black holes. The black holes will evaporate away into radiation. Everything's going to kind of decay into radiation. I talked about the second law of thermodynamics. Everything kind of decays into waste heat, right? And so the universe will be kind of very, very diffuse and with just this little bit of background radiation from all the stuff that's decaying in it. At some point, probably particles will decay. I mean, a lot of particles are already unstable, but protons, we've never seen a proton decay, but we think that those will probably decay eventually as well in some very large number of years, 10 to the 40 or something, the protons will start to decay.
Oh, wow.
And so at some point you get to this stage where there's just kind of nothing left. The radiation from everything decaying will kind of diffuse away, but there'll be a little radiation associated with the kind of horizon of the universe. It's called a de Sitter horizon. It's a kind of, I don't know, shell around us that's associated with the way that the space-time is expanding. But there'll be a tiny, tiny bit of radiation from that. But like the temperature is something like 10 to the minus 40 Kelvin or something, like very, very close to absolute zero.
Wow.
And so the universe will just be this very, very cold, dark, empty place. And because the second law of thermodynamics says that entropy is always increasing over time, the entropy will keep increasing until it gets to like this maximum point, right, where the disorder can't get any higher. Everything is already decayed. And when you get to that maximum entropy point, that's called the heat death of the universe, where heat here is kind of referring to something about sort of the way that the energy is distributed. And it's a death because once the entropy is maximized, kind of nothing important can happen again in some sense. Like there can be random fluctuations. Like you can have it so that some of these photons that are floating around can occasionally randomly run into each other. And you can have particles kind of fluctuating up from the vacuum. And if you wait long enough, then things will kind of appear and disappear through just random fluctuations. But you can't have structure because that would be a decrease in entropy, right? So you can only have very temporary little fluctuations downward in entropy. But, you know, everything is already fully entropized, or I don't know what the word is. Entropic, yeah. And so in a sense, you like not only does nothing important happen probably, but also like you kind of lose the arrow of time. Like time stops having a direction because the way that we define the future is the direction in which entropy is increasing. But if entropy can't increase anymore, then you don't really have a future.
There's no more time.
Yeah, well, there's sort of time in a sense, but it's not passing in any particular direction.
Whoa. Time is just a measure of entropy increasing?
Well, the concept we have as the future is the direction in which entropy increases. Space-time will still exist in this universe.
But isn't the past also just a less entropic universe?
Yeah. So
isn't that's all that time is just whether how ordered things are?
It's a way of defining the arrow of time. It's not a way of defining time itself, I wouldn't say, because time itself is kind of tied up in space-time as a concept. But, you know, when people talk about the arrow of time, like why is the future different from the past? Because in a lot of equations, it doesn't seem like it should make sense. The only thing that really determines the difference between the future and the past is entropy.
Okay. I'm going to try not to let that freak me out.
Okay. Yeah. So one of the cool things, though, about this is you get to this like steady state, basically, where the expansion is just exponential, the entropy is maximized. There have been some suggestions by some theorists that maybe you could have these random fluctuations. I mean, if this goes on forever, then you have this situation where kind of anything that can happen will eventually, right? And just like if you had like a box of gas particles, they're just moving around randomly. Every once in a while, very rarely, but every once in a while, they're all going to gather in one corner for like a split second, right? And it's not going to happen very often, but there's a kind of recurrence time period you can calculate for when that'll happen. And every, trillion years or something, they'll all collect in that corner, and then they'll, on average, right, just from random fluctuations. And so you can kind of do this with the universe. You can kind of imagine the universe as this box of particles, and you can work out like how often it'll happen or how long you'd have to wait for something to appear. So some colleagues of mine, I think Sean Carroll was one of them on this paper. They calculated at some point in this sort of end stage heat death universe how long it would take for a grand piano to assemble itself out of the vacuum. It's just randomly. And they got some number. I don't remember what the number is, but it was very large.
Is this like trying to wait until the little DVD sign, not to date myself, when you would have a DVD in your television and you weren't watching television, there would be like a little DVD sign that would go around the edges of the screen. And then once every great while, it would hit the absolute corner instead of like bouncing off two walls. It would hit the corner. It's kind of like that, but then you've got to wait until all these particles are hitting the corner at the same time to make a grand piano.
Yeah.
But like theoretically, like if everything that could happen will happen, a grand piano will be made. Will a monkey be made? Like, I guess, will biology happen again?
Yeah, so there's a way of calculating this where you can work out like the whole universe will recur. Right. So this is this idea of Poincaré recurrence. You have this situation, this hypothesis that in that sort of setup, if you wait long enough, every point in the past of the universe is contained in this kind of possibility set of things that could happen to the universe. And so, we're dealing with eternities here. This moment right now could recur again, in some vastly distant point in the heat death. Except, in that point, maybe it would be this moment exactly, and then we would just evolve into a new heat death over trillions and trillions and trillions of years. But maybe this moment would occur, but in the future recurrence, I'm wearing a green shirt and you're wearing a red one, right?
Whoa. So that's the power of just quantum fluctuation.
Yeah, or just statistical fluctuations.
Statistical fluctuation and a tremendous amount of time.
Yeah, exactly.
It's like a bunch of monkeys in a room with typewriters will eventually write Hamlet, except the whole universe.
Yeah. And so some people have suggested this as a way of having a new universe come out of the heat death is just you'd randomly fluctuate a Big Bang. But you could also randomly fluctuate any point in time in the universe. But then you get into a problem. It's called the Boltzmann brane problem. This is one of my favorite things in physics. So let's say that you want to randomly fluctuate a Big Bang from this heat death universe. Well, you're much more likely, or much more often, you're going to randomly fluctuate just like a single galaxy, because that's less, that's more likely, right?
Less hard.
Yeah. But then, you're also kind of more likely to randomly fluctuate just one planet.
Totally.
Right, with its atmosphere. And then you're more likely to randomly fluctuate just one person.
Right.
And you're more likely to randomly fluctuate just a brain, just a single human brain that thinks it has experienced the universe.
Right.
And this is the Boltzmann brane problem, because when you work out those probabilities, more likely than we have fluctuated as a Big Bang out of the vacuum of space is that one human mind has fluctuated imagining that the whole universe exists.
Vastly more likely.
Yeah. Which is not to say, that it actually is true that we're imagining the whole universe, but it's kind of just bringing up this contradiction where these calculations no longer are really viable because you're going to hit that we're just imagining it thing before you're going to hit we've actually done it.
That makes my head hurt.
I know, right?
Makes me afraid that I'm trapped in someone else's imagination.
Yeah.
Which I often feel. Right.
Yeah. It's like solipsism is the term, right? It's like this ultimate victory for that concept.
Panic.
But it's really the idea of the Boltzmann brane scenario was brought up just as a kind of way to point out that this is not a good way of doing these probabilities. Right. Because you're going to run into that problem. It wasn't ever a real suggestion.
Right. Okay.
That we are
in a simulation.
Yes. Yeah. Anyway, that's the heat death.
So now we know what happens if dark energy reverses. We know what happens if dark energy is a constant, which is the heat death of the universe, which is a little mind-bendy, but, as endings go, doesn't seem like the worst to me.
No, it's very gentle. It's
that T.S. Eliot poem, This Is How the World Ends, Not With a Bang, But With a Whimper. It's just the lights turn out. It's almost like I was thinking that if I left all the lights in my house on and just walked out of my house for the next 20 years, I'd come back and all the lights would be out. And that's the end of the universe.
Yeah. And I know that a lot of times when I talk about the heat death as an ending, people find it really sad. One of my colleagues, Hiranya Peiris, I interviewed her for the book, and she said that when she gives talks on that, people sometimes cry. Like the idea that the universe fades out and everything ends in cold and darkness. But I think it's, it's the best you can do. And things could be so much worse. You could get a big crunch.
You could have a big crunch and you could see the end coming at you.
Yeah, you'd see it coming. Yeah.
Yeah.
Things could be so much worse. Let us carry that hope with us, even if it is the hope of a temporary species in a temporary universe. How will we ever find peace of mind in a life so fleeting? Well, that is, of course, why there's life insurance. That's right. It's our last episode, which also means it's our last Policy Genius ad. God, I love Policy Genius. With Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options offer same-day approval and avoid unnecessary medical exams. Planning ahead is crucial in life, especially when it comes to what happens when you're gone. And if we've learned anything from this podcast, it's that we will all be gone in the fullness of time. Policy Genius is the country's leading online insurance marketplace, and since they don't have an incentive to recommend one insurer over another, their advice is unbiased. So check out Policy Genius. It's never too late to plan ahead. Head to policygenius.com/crash course or click the link in the description to get your free life insurance quotes to see how much you could save. That's policygenius.com/crash course. Let's briefly recap the first two theories of how the universe ends. First, if dark energy is what's responsible for the expansion of the universe, what would happen if it became less powerful? It's possible that dark energy is decreasing over time, so if it started to lose so much power that it not only stopped but began to reverse, the universe would stop expanding and instead start falling together again. Space would become much hotter as energy is compressed, and we would know the end of everything was coming because we would perceive light as blue shifting rather than red shifting. We call this the Big Crunch, for reasons I am uncomfortable with. I'd much prefer to think of it as a brand of granola or like a breakfast cereal. But what if dark energy didn't get more or less powerful? What if it remained a cosmological constant? Well, we call this outcome heat death, which sounds like a heavy metal band, but is in fact a gentle, quiet way to end the universe. It would continue to expand and everything would become increasingly more diffuse, matter itself becoming essentially negligible. Stars would burn out, black holes would evaporate, and eventually entropy would reach its maximum value and the universe would reach a thermodynamic equilibrium, suffering a heat death, meaning that nothing can really happen anymore. Time stops having a direction, and everything that was going to happen already did. Despite how bleak that sounds, I actually don't mind that one. I'd take a heat death over a big crunch any day. But those aren't the only potential outcomes.
So there's this idea that if the dark energy is some kind of dynamical field, then there's a possibility. And it's not a possibility that theorists like because it messes with certain sort of energy conditions that seem important. But maybe instead of just being constant in space, it builds up in space. So with a cosmological constant, if you define like a sphere, if you just define an imaginary sphere in space, the amount of cosmological constant in that sphere is never going to increase because it's the same amount of space. Even as the universe expands, you've defined, a 1 megaparsec sphere around your galaxy or something, you're not going to get more dark energy in that sphere. So in that case, like if there's a galaxy in the universe, that galaxy is not going to be torn apart by the expansion of the universe because in that region, the matter already won. The matter already is more important than the stretchiness of the dark energy in that sphere. There's not going to be more dark energy in that sphere. So it's a bound structure. It's not going to expand. It's like, the universe is expanding, but this room is not expanding because in this room, the binding energy of all the stuff is more important than the little bit of stretchiness of space, right? So you can imagine a kind of dark energy, they call it phantom dark energy, in which the dark energy increases in every part of space. The density of dark energy or the sort of expansion of dark energy increases in every part of space. And if you work that out, it turns out that that will eventually destroy the universe. And the way it does that is that it builds up within already bound structures. So let's say you have, a cluster of galaxies, they're bound by gravity. If the dark energy is increasing, it's going to kind of pull the galaxies out of that galaxy cluster. It destroys the universe from the outside in the sense of like large scales to small. So if the dark energy is building up in space, first it's going to pull apart things that are like the most weakly bound, so like clusters of galaxies. Then it'll start getting to galaxies, so it'll start like pulling apart, taking stars out of galaxies, sort of unraveling galaxies. Then it'll go into solar systems. It'll take the planets away from the sun. And then as it continues to build up, it can start breaking apart solid objects. So you can break apart the Earth and then break apart, atomic molecular bonds. And then eventually you get to a point, and you can calculate for a given model, you get to a point where the scale factor of the universe goes infinite. So the scale factor is a number that tells you about like the size of the universe, how much is expanding. So, the scale factor today is 1. Some number of, billions of years ago, it was 0.5. The universe was smaller. That kind of just scales like how big space-time is. So in a finite time, you can calculate the scale factor will go infinite, which just means that the space is expanding so much that it just completely rips apart. And that's called the Big Rip.
That's called the Big Rip, which is another really good name.
Yeah.
I just think we need to compliment the far future cosmologists as opposed to the far past cosmologists for just in general doing a better job with naming.
Yeah.
No inflaton
right
business. Just no removing a single letter from a word and thinking you've accomplished something. So anyway, and I'm sorry to the person who coined inflaton. I'm sure they're a nice person, but it's not a great name, and I wish you'd consulted with me. So in this case, in this Big Rip case, the size of the universe, like the scale of the universe, becomes infinite in a finite period of time.
Yeah.
That is really, really hard to get into my head.
Yeah. And there are reasons why theorists don't like this scenario, because in order for that to happen, you have to break these kind of energy conditions that we think exist in the universe that prevent stuff like that happening. But if you just put in dark energy with certain characteristics, then you get something that looks like that in the simplest versions of the equations.
Okay. When
we measure the properties of dark energy, it seems to be completely consistent with a cosmological constant for the most part.
Okay.
But, you can't quite rule out a phantom dark energy, this stuff that would cause a big rip, in terms of just the observations, just what you can measure about the equation of state parameter of dark energy, which tells you about kind of how this stuff works. And so you can work out like what the error bars are on the measurement of this, like how uncertain we are about the measurement of this. And in doing that, you can get like a calculation of what's the soonest the big rip could happen if it were going to happen. If dark energy really is not exactly a cosmological constant, but this stuff that gets more powerful. And when you calculate that, we've got at least like 200 billion years. So just based on the way that we can do our calculations. So, 200 billion years, like that's after we already can't see galaxies anymore. So it's like, there's not a lot to rip apart at that stage, right?
I don't know. There's something like, and I know that it won't happen on this scale, but there's something terrifying about looking up into the sky, seeing absolute darkness, and then like slowly having dark energy rip apart your solar system and then your body.
That's true. And you can't escape it because it's just space that's doing it, right? So like no matter, you can't like protect yourself from it, like being in a protective casing or something. It'll rip the casing apart.
It's just something that's going to happen. That's a little terrifying.
It is a little bit terrifying. And again, you would see it coming, so that's not great.
So if I'm going to rank these first three, I'm going to say Big Crunch is the worst.
Yeah.
Heat Death is the best. Mm-hmm. Big Rip is the second worst.
Yeah, I'd say that. I'd agree with you on those.
Now, there are two more ways that you wrote about that the world might, the world will be long ended. The universe might end. Walk me through those.
Okay, so the next two are vacuum decay and cyclic cosmologies. I'll start with vacuum decay because that is my personal favorite.
Okay.
And part of the reason it's my personal favorite is because technically it could happen at any moment.
Oh, great. I'm glad that's your personal favorite.
Now, and when I say this, I need to give a disclaimer, which is that it almost certainly won't.
Sure.
And please, do not write us emails being sad about this and scared, because this is not a thing to worry about. But just to the audience, because I do get emails from people who are scared about vacuum decay, and it's really, I'll explain why not to worry about it. But let me just first walk through what the idea is. So we talked a while back about the Higgs field. So there was this event that happened in the early universe that altered the Higgs field. So the Higgs field is this energy field throughout all of space. It's a scalar field, like we think caused inflation, like dark energy could be. It's this sort of energy field through space, and it's connected to how particle physics works in our universe. And like the state of the Higgs field, what kind of value it has, and what kind of number is associated with that field connects to what particles can exist in the universe, whether they can have mass, all of that stuff, the setup of the standard model of particle physics. And we think that we're pretty sure that in the beginning of the universe, the Higgs field was in a different state than it is now. There was a transition that happened, and that transition allowed for particles to have mass. It allowed for the particles of the universe in the standard model of particle physics to exist. It allowed for us to have, chemistry and bodies and all of that kind of thing, right? Molecules could exist. There is some suggestion based on data that it's possible the Higgs field could change again. And this transition would be like a quantum tunneling event. So quantum tunneling is where if you have like a particle on one side of a barrier, like an electron on one side of a barrier, if you wait long enough, that electron is just going to appear on the other side. Even though it didn't go through, it didn't go around. It's just that there's some uncertainty that's built into quantum mechanics about where that electron is. And that means that some of the possibility for where it could be is on the other side of the barrier. And so if you wait long enough, that's where you'll see it. That's quantum tunneling. And there's kind of a similar uncertainty that kind of works into the Higgs field where it might show up in this other part of its potential, which is the potential is like the sort of physics governing what state it could be in. So it could just kind of show up at a different value through this quantum tunneling transition. And the thing about quantum tunneling is that it's inherently unpredictable. You can calculate like a decay rate. Like if you have a radioactive particle, you can calculate the half-life of that particle, like how long, or a substance, you can, how long it'll be before half of that substance is decayed. That's a half-life, and that's governed by the same kind of physics. So we can calculate like a half-life for the universe for this transition of the Higgs field. But we can't say exactly when it might happen or where, if it is governed by this quantum tunneling transition. And the way it would work if that transition happened, if you did have that transition happen somewhere in space, is that, somewhere in space where the field does that quantum tunneling event, then the Higgs field would go into this other state that's called a true vacuum. So we have the current Higgs vacuum. Vacuum here just means like the state of the universe, not nothingness, but the state of the universe. You talk about different kinds of vacuums. So vacuum is just like the background state. So potentially we're currently in a false vacuum, meaning that it's like not the sort of preferred state of the universe, and we could transition to a true vacuum. It's possible the Higgs field is what is called metastable, which means that there could be a transition sometime in the future where the Higgs field could change to another state. When we say the universe might be metastable, we mean that it's kind of stable for now, but it's stable in the way that like if you take like a cup and you balance it at the edge of a table, so it's like really close to the edge, it's still sitting there, but like if it were nudged just a little bit, it would fall over, right? And that's metastable because that cup would really rather be on the floor in some sense, right? Gravity says that it's better on the floor. So there's like this gravitational potential, which is like the shape of, what the gravitational field is at different points. And that just says that the cup would rather be on the floor in some sense. And so it's possible that that's the way that the Higgs field is set up, that it has some potential, some kind of thing governing what state is more favorable energetically for the Higgs field. And the state that it's in right now is not the most favorable state. And so that means that, like, it's there for now, but if it could be nudged, it would fall into that other state.
Which is a true vacuum.
Yeah, which is the true vacuum. So, and we don't know any way to nudge it, so.
Well, I'm glad we don't know any way to nudge it because I don't trust us not to nudge it.
Yeah, no, I've worked on trying to figure out if there is a way, and I don't think there is. But
good.
Yeah. But because the universe is fundamentally quantum mechanical, it actually applies to the cup balanced on the edge of the table, too. If you wait long enough for a cup balanced on the edge of the table, all the particles in that cup are going to quantum tunnel through the table and it'll fall to the floor anyway. Like, it's a ridiculous amount of time that you'd have to wait for that to happen, and the cup would probably, like, decay away anyway before that. But in principle, that could happen through quantum tunneling. And so the same kind of applies to the Higgs field, where even if it's in this sort of better false vacuum state, if there is a true vacuum that's at a lower energy state, basically, then it'll eventually quantum tunnel into the true vacuum. And so when that happens, what happens is that at some point in space, a quantum tunneling event occurs where the Higgs field goes from being in the false vacuum to the true vacuum at that point, and then it spreads because that's the more favorable configuration.
That's the way it wants to be.
Yeah.
That's the better situation for it. How fast does that happen, Katie?
So once that bubble of true vacuum nucleates, once it starts, that bubble expands at about the speed of light.
Oh, so fast.
Yeah.
Well, depending on where it is.
Right.
Would we see it coming?
No.
Oh, fun. Because it's the speed of light.
Yeah. So by the time the light from it gets to you, it is on top of you also, because it's traveling at the same speed.
So in that case, let's just say this happens, and I understand that it's very, very unlikely. It's like vanishingly small likelihood that it's going to happen anytime soon.
Yes.
And so we shouldn't worry about it.
Yes.
We have lots of real things to worry about, so we shouldn't worry about these tiny hypotheticals.
Yes.
But let's say it happens in 500 million years, which I know is unlikely. But let's say it happens at some point in the next 500 million years, so that we still have a chance of being around, albeit a very small chance. In that case, we'd all go out together, right?
Yeah.
Like, we'd all go out within a fraction of a second of each other.
Exactly.
And we'd just sort of be sucked into this true vacuum. I like that one.
Yeah, yeah. So the way it would happen is the bubble would have like a bubble wall that's like got some sort of high density, like it's kind of high energy radiation or sort of on the edge. So first that bubble wall would probably incinerate you, but then you're inside the true vacuum. And then in the true vacuum, we don't have the same chemistry. Your particles don't hold together anymore. You're fully disintegrated. And then it's possible that the space inside the true vacuum also collapses to a black hole. So it's like you're very, coherently destroyed. But it happens very fast, right? Because if this was traveling at the speed of light, like you wouldn't see it coming. You also wouldn't like feel it or notice it because the speed of light is faster than your nerve impulses can travel, right? So you kind of don't know it happened. Like you don't know it happened. You don't feel it. It would be like blinking your eyes and just never opening them again. But like you don't know that happened, right? So it would be very clean, very painless. And everybody, the whole universe, like within that bubble would be destroyed altogether. So there's no tragic aftermath, there's no FOMO. Like it's just done.
Yeah. # no FOMO.
Yeah. Yeah. I think it's a very humane way to end the universe, honestly.
It seems pretty clean to me, and that's appealing.
Yeah. Yeah.
Great. Let's do that one. Do we get to pick? I guess we don't get to pick, but if we can, let's do that one.
But so the idea that we live in a false vacuum is based on measurements of things like the mass of the Higgs field, or the mass of the Higgs boson and its connection to the Higgs field, the parameters of the standard model of particle physics. So we don't know if there's other physics. Like we think probably the standard model of particle physics is not like the final word on, what the universe is made of. And so it's possible some other physics will come in that changes that picture. But based on our current estimates, if there's no other new physics that comes to change that picture, the sort of decay time of the universe is something like 10 to the power of 100 years, maybe 500. So really, really long time from now, long after everything important has happened in the universe. So it's very unlikely it would happen anytime soon. And when people say that they're worried about it happening, I tell them, like, you're much more likely to, like, get struck by lightning while also being eaten by a shark and winning the lottery. Like the probability is adding up here. Like, it's very, very unlikely to happen in our lifetime, like, to an astonishing degree, even if we're right about all the physics and there's nothing beyond the standard model. So I definitely don't think we should worry about it.
Okay.
But it's a it's a fun thing to think about as a physicist because it's this cool connection between like fundamental particle physics and like the existence of the universe. And I find that just really compelling to think about, really fun to think about.
Yeah, no, I hear that.
So maybe dark energy isn't a constant in space, but instead builds up, becoming the spookily named phantom dark energy. And if that was the case, well, that could also eventually destroy the universe. If that dark energy increases, it would destroy everything in the universe from the outside in, unraveling galaxies, ripping apart solar systems, and eventually breaking up solid objects. This theory is appropriately named the Big Rip, and we would see it coming. But what if the end of the universe has nothing to do with dark energy at all? What if the culprit was vacuum decay? The Higgs field, you'll remember, is an energy field through space and is directly connected to how particle physics works in our universe. In the beginning of the universe, we think that the Higgs field was in a different state than it is now. And with that knowledge, there's some suggestion that the Higgs field might change again. And this change would likely be triggered by a quantum tunneling event where a particle moves from one place to another through apparent barriers. Upon this change, the Higgs field would turn into a true vacuum, the state it was leaning toward all the time, destroying the universe in the process. Now, at least in this version, not only would we be blissfully unaware of that destruction happening, it would happen to all of us practically in the very same moment, a kind of united, instantaneous farewell. But we still have one theory left, so I'll let Katie take it from here.
All right, so we've reached our last future. This is the one that I want to be true. Because what I want, and this is irrational and I don't even know why I want it really, like I'd have to deeply inquire with myself, but I want something of our universe to survive into the next universe.
Yeah.
I want something of us to be eternal, some memory, obviously it won't be us humans, but I mean some memory of our universe to be preserved into the next universe. And if there's some kind of cyclic cosmology, as there is in some religious traditions, like in Hinduism, other religious traditions, if there is some kind of cyclic cosmology where our universe is somehow in its ending births a new universe with some memory of us, that's the most, I guess, like symbolically appealing one to me.
Yeah. So there are a few hypotheses about cyclic cosmologies. And generally speaking, they're hypothesized not really to talk about the end of the universe, but to talk about the beginning of ours. So there are some weird technical problems with what we think might have been the initial conditions of our universe. And we use the concept of cosmic inflation to explain some of the initial condition issues, but there are others that have to do with like entropy that are a little bit more difficult to tackle. And so some theorists have come up with ideas where a previous universe ends and starts ours, and something from the previous universe sets up the conditions for our current universe.
Okay, yeah.
As a way of explaining how our current universe got here the way it is. And so, one of the ones I talk about in my book is an idea from my PhD advisor, Paul Steinhardt, and his colleagues, who talked about a universe where there would be a contraction toward the end that would be not a full big crunch, but a contraction to a smaller universe that would then re-expand to a new universe, and there would be a cycle of those kinds of universes, and some information like gravitational waves or something would be preserved through this, and it would kind of set up the conditions for the next stage. There's also Roger Penrose, who recently won a Nobel Prize for his work on gravity and things. He has this idea called conformal cyclic cosmology, where the universe ends in a heat death, and then there's a new Big Bang that comes out of that heat death, and there's information that passes through that transition, basically just sort of where the supermassive black holes are, but like some kind of information can get through there. And there are other models where a sort of previous cycle sets up ours. It was really interesting when I was working on this book and talking to people about these kinds of models where, I kind of get this feeling that, like you, some of the people working on these models like the idea that something persists of our universe, that it's not fully forgotten, because I think that that's something that, these models are, I don't have a whole lot to say about them because they're still kind of being developed and they're not as, accepted as other models because, for one thing, they're still being developed and also in some cases they don't fit the data as well or they're, the data isn't there yet to distinguish. But you definitely get the feeling that, some of the people working on this are saying like, it can't just be all over when it's over. Like there's something has to come through. And I like this idea that there is some persistence.
Yeah. Well, this is something that I find really interesting about physics is that it's done by humans.
Mm-hmm. Yeah.
There's no way to separate our humanness from our scientific inquiry on some level because we're the ones doing it. And it's not just that I want gravitational waves from our universe to survive into another universe. It's also that, like, it just makes sense to me on a basic level that in some way they would. It just tracks with other things I've observed in the universe. So I understand that urge. But of course, like, I guess when we're making scientific inquiry, we try to push aside our biology as much as possible.
Yeah, it's interesting. Like, there's another sort of setup that's not really about the end of the universe, but about the beginning where inflation, this cosmic inflation process, could have happened multiple times. It could be happening in lots of different parts of this much larger universe.
Yeah, almost like a blanket of things and the little pieces of it become universes.
Yeah, little pocket universes come out of that. We talked about that in the inflation episode. And that's another situation where, our universe will reach a heat death, maybe, but other universes might just be starting in other parts of this larger space, larger multiverse. But whether or not there's any memory of our universe is kind of unclear in that kind of situation.
Right.
One of the things that's really interesting to me about thinking about these different possibilities for the end of the universe is like when people think about, like, I don't like the idea of death, right? I find it very uncomfortable to think about dying. Yeah. Right? I don't want to die. I don't want anybody I care about to die. Like, that idea of permanent ending is unsettling to me. And so you might think it odd that I wrote a book about the end of the universe. I had to spend about 2 years thinking about the permanent ending of absolutely everything, and that's not comfortable. But it's kind of like the end of the universe is not so personal as the idea of me dying. But there's a sense in which it's kind of worse for, like, when you think about dying, right, which you don't want to think about when you do, like, one of the ways that people become comfortable with the idea of dying is that they think, well, something of me will persist, right? My children, my great works, the mark that I made on society, something will be left over from me. I will have made the world better in some way. I will have had an effect. I will have had some kind of impact.
Yeah, like you're a little pebble that gets thrown into a lake and then you ripple out even after the pebble has sunk.
Yeah. And even if it's like just the sort of butterfly effect version of like just having existed changes the universe in some way, like you've mattered, right? And when you think about the end of the universe, you kind of lose that because if the universe is really ending, then at some point it will not have mattered that we existed, any of us, right? There will be no memory of that, no persistence of that. And so at some future point, we will have all been erased. It will not have mattered that we were ever here. And that is much more unsettling.
Of course, yeah.
And that makes it hard to, think about like something that kind of makes it all worthwhile retrospectively, right? Where the ending kind of justifies what we all went through, which is a very popular thing in fiction, but also religion. This idea that like, yeah, everything was hard or whatever, but it turned out great in the end. We got our just rewards, whatever. Like, it's meaningful in retrospect.
Right. That's how we tell stories. There's also some truth to that on a micro level, right? Like, there's some truth to the idea that love survives death. Like, my grandfather is dead, and yet the love that we shared is still here.
Yeah, right.
But the end of the universe, knowing that there will be an end to the universe, which we've really only known for a few generations of human history, right? Like, this is a tiny fraction of human history. If we think about the history of humans as being a calendar year, begins 300,000 years ago, and today is 12:59 p.m. on December 31st, like, we've known that the universe was going to end for like 3 minutes.
Yeah.
And so it's new and it's upsetting to me because we're this weird species that is finite but can conceive of infinity. And so, of course, we want to be able to live in that infinity somehow, some way. And this says you just won't.
Well, and even not being able to live it, like, we're so used to creating meaning retrospectively, right? To assigning purpose after the fact. And you can't do that if there is no after the fact.
There's no final victory because the final is the lights turn off.
Yeah. And I know that a lot of people get some sense of meaning through thinking about it that way, through religion, where they think, like, I'll get my reward in the end, or God will sort it all out or something. But if you're just thinking about, like, the physical existence of the universe, you don't get it from that. And so for me, I've found that thinking about it in these terms really made me think about the necessity to create meaning in the moment, right? To decide that this moment is meaningful, even if it is forgotten, right? That living life in the moment, not with regard to what it might all turn out to be in the future, which I obviously cannot predict. It's important to have it meaningful right now.
So your feeling is that since there will not be a time at which we're able to look back on all of this and say, well, the suffering and the misery and the injustice was justified because of X and Y and Z, it matters more, not less, to try to decrease suffering and injustice now.
Yeah, and to try to appreciate joy now.
Yeah.
This is a little bit personal, but when I was writing this book, my grandmother passed away. And I had been reasonably close with her, but I had moved away and I hadn't seen her very often. And in the kind of the way everything worked out, a lot of her sort of personal possessions went somewhere else and I didn't know where. And there were things that she had that I knew that she wanted me to have that I didn't get in that process. And I was very sad that she had passed away, and I was sad that I didn't have mementos from her that I had hoped to. But when I thought about that and I remembered her, I thought, like, well, everything is going to end eventually anyway. We don't get to keep anything anyway. And what really mattered about that relationship was that when I was with her, we had joy, right? And I'm going to die. She died. Everything we have is going to be destroyed in some way in the future, but it was still meaningful. And the important thing was the time that we had in the moment. And that kind of helped, which was a little surprising to me, but it kind of helped to think, well, everything is going to end, but that doesn't mean that it's not meaningful in that time. And it made me think about, like, really appreciating joy and love and connection when it's happening.
Right. I mean, it was meaningful not only because you had that joy, but also because you shared that joy between the two of you.
Yeah.
And I think that's where I land as well. It's that you have to find meaning, whether you are constructing it or trying to derive it from some higher source. It doesn't really matter to me, but you have to find meaning.
Yeah.
And you have to find meaning together. You have to find joy together. It's not just that you want to have it, it's that or that you need to have it, you need to seek it, but you also need to share it.
Yeah. Yeah, definitely.
I've been going through a really hard time, Katie. I've been really struggling with serious depression. And it's interesting to think about it in that context, because my impulse has been to pull back, to not share as much, to not talk about it, not, just try to deal with it myself, because I don't want to burden anybody. I don't want to be a problem for anybody. I don't want to make anybody's life worse. I don't want to increase the amount of misery in the world by talking about it.
Right.
But maybe actually these things are better when they're shared.
Yeah.
And we find more meaning and connection in the moment when we're able to share what we're going through.
Yeah. Yeah, I think so. I think that, having other people having those connections is a temporary thing. Someday the universe will be empty and cold and dark and we'll be alone in it. And I don't know, I think that making the most of human connection and building meaning together in the moment is really important.
Yeah. Well, I have to say that being able to have these conversations with you and learn from you has meant a lot to me, not only because I didn't know anything about black holes or dark energy when we started, but also because it's a way of sharing meaning and understanding. And I really appreciate your generosity in sharing that with me and with everybody listening. It's been an extraordinary journey, and we now know that it will end in perhaps one of 5 ways, but not yet.
Yeah.
Not today.
Yeah. And I've really enjoyed this. It's just been great to talk with you about all this and to see it from a kind of different perspective and to share it with people through this podcast. So I found this to be very joyful as well.
Me too. Thank you.
Thank you.
And thanks to everybody for listening.
So the beginnings of our universe may hold the answer to how a cyclic cosmology might occur, bringing some parts of our universe into the next. The universe could contract, then re-expand, another Big Bang could occur. In that vast future, there may be a memory of us, or there may not be. We just don't know. But we are here now. We know the warmth of our sun, and we know much about the warmth of other suns. We can see tiny particles that make us up, and we can see ourselves as tiny particles in a vast universe. What a gift to be here for and with each other. What a gift to begin to fathom the universe in which we find ourselves. Maybe there won't be a memory of us in the long, long universe at all. But to me, there's something wildly beautiful about the fact that while we cannot live forever, and while our universe probably won't be forever, we can still engage with and imagine the infinite. It's easy to grieve for the loss of us, the loss of our planet, our solar system, our galaxy, and I don't blame myself for feeling that grief. It's hard not to feel sad, knowing all of this will end. But not yet. Not yet. Thanks for coming on this journey with us. Thanks for being a co-discoverer of the universe. This show was hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, with music and mix by Joseph Tuna-Medish. Special thanks to the Perimeter Institute for Theoretical Physics. Our associate script editor was Annie Fillenworth. Our editorial directors were Dr. Darcy Shapiro and Megan Modafferi, and our executive producers were Heather DiDiego and Seth Radley. This show was a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.